Hi, good evening, everyone. My name is Bhabya Rai. Welcome to the final week problem solving session, okay, for computational complexity. And this week's topic is interactive proofs. So we are nearing the end of the the computational complexity course on NPTEL. I mean, although the subject itself is more vast, and what we've covered is sort of a breadth first attack on the content, but we've covered the basic parts that make up complexity theory, okay, to quite a certain extent. So finally, we are looking at what are called interactive proofs. So also before continue with the session, I would like to make an announcement. That is that tomorrow, that is Wednesday, 16th of October, from 4 p.m. to 5 p.m., I shall be holding an extra problem solving session. Okay, it is not exactly a problem solving session in the sense that I won't be solving any questions there unless you have a particular doubt that I may attempt on. Otherwise, what I'll be doing is I'll be giving a quick summary of what we've covered so far. So this may help you in the exams. And furthermore, if some of you are more interested in looking into this topic of complexity theory more in depth fashion, then I shall actually cover a few of topics which are, uh, which are at the forefront of uh, research in complexity theory. So, what are the hot topics right now that are being researched about? And and what are the top people in complexity theory actually attempting at? What are the current open problems, and what is the progress so far? So a few of those questions which were not covered in this course, I would like to actually introduce them to you. And of course, then if you have any other questions which are maybe closely or even vaguely related to complexity theory, then I'll be happy to tackle it. But that is it. That is the announcement. So please make sure you attend it if you found it interesting. But I either way, I highly recommend that you attend this session. It will be a short session. It'll just be for 1 hour, 4 to 5 p.m., and then we'll be done about it. Okay. Okay. So let's start. Okay. So this week we are dealing with interactive proofs. Proofs. Okay. So we've already seen something like interaction, okay, something that is close to interaction, which is communication complexity, right? You had Alice and Bob, right? So what did you have in communication complexity recently? Okay, you had Alice and you had Bob, and they were trying to compute a single function f of xy, right? Alice was given some x, Bob was given an input y, and they were communicating bits. And finally, they both came up with f of x, y. Okay, and the number of bits exchanged between Alice and Bob was what is called the communication complexity of the function, of the protocol, and the minimum number of bits needed to compute the function f is what is called the communication complexity of the function f. Okay, now we sort of think of this approach. We sort of mix two kind of approaches. Okay, we borrow something from proof verification, okay, which is closely related to the idea of NP. Okay, and we talk about interaction. Okay, so this is called interaction. You have two parties and they are exchanging information with each other. So Alice and Bob are interacting with each other, right? So now we borrow this idea and mix it with the idea of NP. Okay, so what is NP? Okay, what is NP? NP is the following. uh, and NP, what is NP? We say X. Okay, so a language L, okay, is an NP if, right, there exists a deterministic polynomial time verifier, okay, and I'll call it V, verifier Turing machine or verifier algorithm V, okay, such that um, if there exists, if X belongs to the language, then there exists a certificate Y, okay, which is okay, but which is there exists I'll call it small size certificate, okay, or poly size certificate, okay, Y. There exists a poly size certificate Y such that V of X comma Y equals 1, okay, and this is only in one direction, right? We what we need is an if and only if, and if X is not in L, then no matter what certificate you give me, okay, no matter, for all polynomial size certificate, okay, for all polynomial size certificate, no matter what certificate you give me, for all V of xy is equal to 0. So now what do you do? Okay, so here's the idea. Okay, here's the idea. Here's the idea. Now what you do is, okay, um, here I have a verifier machine. Here I have a verifier machine. Okay, and suppose x belongs to L. Then there exists a y, right? So maybe I give it a certain y1, and it will say no, this is not the y I need. And this next I say y2, and then it says no, it is not. But eventually I will land up upon a good y such that it'll say yes, y is the certificate. So yes, x is in L. So this is one way to imagine this, right? And now question is, let's say this L belongs to NP. Okay, L belongs to NP. Okay, and question is, can I fool this verifier? Okay, can I fool this verifier? What do I mean by fool it verify? Fool the verifier. I mean, what I mean by can I fool V? Can I fool verifier? What does that mean? I mean that that is X actually does not belong to the language. Okay, but give but give a Y such that the verifier says yes, okay, it belongs to the language. Is that even possible? That is the question. But our answer is immediately no, that is not possible. Right? Why? Because it violates the definition of NP. It violates the definition of NP. What does NP say? It says for all x in L, um, give me any certificate. It does not mean that give me any certificate. It will never be. The verifier will always be able to catch you if you try to fool. Okay. Now this is the general idea. Now, so this is NP. This is the new view of NP. Okay, this is the new view of NP. Now what we are trying to do is we are trying to do the following. Okay, with this new view of NP, what we are trying to do is we are trying to generalize NP. Generalize NP. Okay. Now, what is NP? NP says you have a verifier, and there exists a Y. Okay, which is sort of the proof that X is in L. This is sort of the proof. Okay, and then it sends it to the verifier, and verifier says either yes or no. Okay, so if I'm giving it to the verifier, I am trying to prove that X is nil. If I'm trying to give the certificate, correct certificate, I'm trying to prove that X is nil. Okay, so that's why I'll call myself the prover. Okay, and I'm trying to prove that X is nil by giving it the correct certificate. Okay, and I'll give it to the verifier. Now it is up to the verifier to say yes or no. Right now, so now what I'll do is actually here is my generalization. Um, what if what if I allow more than one round of communication, or in this term, interaction. What if I allow more than one interaction? That is, what if I keep sending? What if now my prover, now it makes sense to call it the prover, I'm trying to prove that X belongs to the language, can give several certificates, okay, Y3 and so on. Or it may even give it bit by bit, right? And the verifier will say no, 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 and so on. And maybe at one point it'll say yes. Or it may not even be like one certificate after another. It may be one bit after another, such that the entire thing is a single certificate, something like that. But you see that this is a generalization of NP, right? Now, question is, okay, and not only this, sorry, not only this, verifier is himself allowed to ask questions. Okay, y1, let's say this is q1, y2, q2, and so on. Not only this, the verifier himself or herself is allowed to ask the question. Now, what will now question is this model more powerful than NP? Right. Now, sadly, okay, answer is no. Now, why is it not more powerful than NP? Because NP himself can simulate this protocol. Okay, so because NP can simulate this, now you have the prover, you have the verifier. Okay, now let's say so one direction is simple. Okay, one direction is simple, that you can simulate NP with this protocol. Okay, now what about the other direction? This protocols can simulate NP. Why? Because the fact that this protocol, let's say this, for that particular language, the protocol can do with multiple rounds. Okay, and and so on. Right. This is what letter did I choose? Y1, Y1, Q1, Y2, Q2, and so on. And remember that verifier is always deterministic. I mean, not always, but the fact that this was a generalization of um, the generalization of NP means that verifier is deterministic. Now, since verifier is deterministic, what does it mean? The questions we ask is predetermined, right? The questions that verifier asks is predetermined. So I know that he's going to ask Q1 first, and then Q2 first, and so on. and so forth. And assuming that there are polynomial number of rounds, okay, um, okay, this I didn't specify. We are assuming that we are allowed more than one round of communication, okay, at most polynomial, okay, number of rounds. Then what I can do is then simply send y1 dot y2 dot y3 dot and so on till ym, right? So simply send this. I already know that it's going to ask these questions, so I'll send y1, then y2, and so on. So each of these clubbed together will form a certificate, because otherwise the definition of this protocol and this is identical, right? So and this forms my certificate. And there are polynomial many rounds, and the verifier himself is deterministic as well as taking polynomial time. Okay, then it takes this much time. So now we formally define it and see that, okay, now this is not more powerful than NP. In fact, we just saw that it is exactly equal to NP. Okay, so let's see DI, this, what is this class called? Okay, DIP, or deterministic interactive proofs. Okay, so what is a deterministic interactive proof? Well, a language L is in is said to be in deterministic IP, okay, if um, there exists an interactive protocol or interactive proof, okay, of polynomial length, okay, that is able to convince polynomial length such that, okay, if x okay, and a deterministic polytime verifier, okay, interactive proof and a deterministic polynomial time verifier such that if x belongs to L, okay, then there is a proving strategy, or there is a prover. So one prover works in a certain way, the other prover works in a certain way. There exists a prover, okay, P, okay, if x belongs to, there exists a prover P, uh, such that the verifier, okay, um, when it takes the proof of the when it takes the proof of the prover, okay, it outputs one. So this is what is called the soundness, or the correct, sorry, not the soundness, the completeness, okay, also called the, yeah, completeness. Okay, what is completeness? Well, it says that, okay, if a solution exists, then you should always say yes. But what about if x does not belong to L? You should be able to say no, right? The verifier should be able to say no. So then for any prover P, or any proving strategy P, V of P of x is equal to 0. So this is what is called deterministic interactive proof. Okay. So because why is this deterministic? Why is this deterministic? Verifier is deterministic. Here, deterministic polynomial time verifier. Okay, the verifier is deterministic, and this is why this interactive proof is called a deterministic interactive proof. Okay, now you have this now. Okay, and this part is called soundness. Okay, good. Now we have deterministic interactive proofs. Now what did we just saw? What did we just see? We saw that NP is equal to BIP. So now the question is, even after generalizing NP, we stay at the same place. Okay, there's nothing non-trivial happening. Now what we do is we want to see if we can obtain a model which is more powerful than NP. Okay, to justify it as a generalization of NP. Okay, otherwise this is not a valid generalization of NP because it is as powerful as NP. Okay, not more. So now what we can do is, okay, make the verifier deterministic. Sorry, it's already non-deterministic. So sorry, it's already deterministic. So make it non-deterministic, or actually even better is make it actually probabilistic. Okay, because it does not make sense what I mean by non-deterministic. So what do you mean by probabilistic? I mean randomized. The verifier is actually allowed to toss random coins. Okay, so now what do you do? Yeah, verifier is probabilistic. Okay, now what do? I just take this definition. How do I copy it? Okay, and now I rename it as IP and I write it as interactive proofs. Just okay. Okay, I call it interactive proof. Now L is said to be in IP if there exists an interactive proof of polynomial length. Okay, and okay, sorry, this okay, polynomial length means polynomial rounds. Okay, so I'll not write it length, I'll write it rounds, and I'll actually generalize this to IPK. Okay, so with key rounds and a deterministic polynomial time verifier. Now this I want to change. I'll write it randomized polynomial time verifier. A randomized polynomial time verifier V, okay, such that if x is in L, okay, now I have random bits involved. Okay, now I have random bits involved. So verifier is probabilistic. So now what I do is, if there is a prover P such that the probability over the random bits, okay, over random bits, okay, I'll just write R tossed by V, okay, means that the verifier will actually accept with a probability 2/3, at least 2/3, and the prover P such that no matter what prover I give, okay, proving strategy I give over the random bits, okay, the probability that it rejects is greater than 2/3, or the probability that it accepts is less than 1/3. Okay, so now why is this helping? Okay, because possibly it may not be feasible that every time I am able to correctly verify whether the prover is correct or not. But it may be so that for a large for a large Yeah. Hi, Suraj. Are you able to hear me?
Yes, sir.
Oh, okay. My volume is very low. Okay. Yeah. Uh, yeah. Okay. So yeah, I'll just get back to this section. Okay. So I was just talking about how IP is a generalization of NP, and finally defining IPK. Okay. What we have K in IPK is that uh, now the verifier is non-deterministic. Okay. And so I have this prover and I have this verifier and I have a language L. Okay, I want to say whether X is in L or not. Then, if X belongs to L, then I have a proving strategy such that the verifier, okay, will toss some coins. Okay, it has access to some random bits. Okay, and for a large fraction of these random bits, the verifier will accept. So, arguably, considering the verifier to be a probabilistic machine, I have an advantage here. Okay, so that is what it is. Now, and if X is not in L, then for all proving strategy, okay, I will fail to prove it. Okay, prove that verifier accepts with a for a large fraction of the random bits. So this probability is over. Okay, and no, not fail to prove. I will successfully prove. Sorry, that it does not satisfy. Okay, but anyway, so that is what IPK is. Okay, so IPK means k rounds of this. So what if I generalize this? Okay, that is IP poly. Okay, on the input. Okay, I'm being a bit loose with the notation. A proper notation would be um, union of n to the c. Okay, n is at least 0. Okay, so this polynomial. Okay, um, this is equal to IP. So IP means a polynomial round protocol such that if X belongs to the language, then what we have is the verifier, okay, which is already fixed. Okay, that verifier will be will accept with a probability because the verifier is probabilistic now. Okay, verifier will accept with a probability at least 2/3. Otherwise, for every proving strategy, it will say that okay, no, the X does not belong to language with a probability at least 2/3. Okay, now why is this interesting? Because this was actually first studied, and actually it is still studied mostly in the field of cryptography. So what is cryptography? It deals with building secure systems. So there are a lot of concepts, like one-way functions, and you have quantum cryptography, quantum algorithms, and so on and so on forth. And you have something called zero knowledge proofs, which you can check out later. Okay, and this zero knowledge proof, actually the idea stemmed from this interactive proofs. Okay, and interactive proofs also, and they also have something called MIPs, MIPS. Okay, which is multi-party interactive proofs. So there are multiple provers now. Okay, now these kind of things are studied in cryptography, and that is why there was a primary interest in why this interactive protocol is interesting. And of course, we as complexity theorists have a different way of thinking about why this would be interesting. Okay, first thing is that it is a generalization of NP. So the same idea of NP, if it generalizes, then it becomes this. Now we can view IP as a different model of computation altogether, and we want to ask questions like how powerful is IP? Is there a limit to its power, or what kind of things can be solved in IP? Okay, and now why cryptography? Because we have this prover and we have this verifier. Okay, and if your prover is honest, okay, if your prover is honest, then verifier should be able to say yes, yes, your proof is correct. Okay, your proof is correct. And if your prover is a cheating prover, okay, if your prover is a cheating prover, I'll call it P1, P2, then it should be able to say no. So I think you can already see why this why this kind of protocol is actually useful in cryptography. The P1 can be seen as a sort of a passkey, and the verifier is your authentication algorithm. Okay, so it'll give you a passkey P1, and you want to check whether the passkey is correct or not. If he is honest, then yes. Otherwise, for if he is not honest, then no matter what kind of prover you give me, no matter what kind of proof you give me, I'll always say no. So this is a very interesting take on it also. Okay, so and so that is what a proof means also philosophically. Now, yeah, so where was I? Okay, so we are talking about the complexity theoretic view. Okay, okay, question is, how powerful is IP? Earlier we already saw, and in the lectures also we already saw that NP is contained in DIP, right, deterministic IP. And this hi uh, so we okay, how powerful is IP? We already know that NP is contained in deterministic IP, and deterministic IP itself is contained in IP. So we know that IP is at least as powerful as NP, right? So now we can ask other questions like, do we know any upper bounds about this? Do we know any upper bounds about IP? So what we can say is we have one upper bound, okay, and we'll show it later. Okay, that is that IP is contained in P space. Okay. Yeah, Suraj, IP is equal to P space. We'll see one direction of the proof in some time. Good. Okay, and so that is the other question, which is very interesting. Right. Now the next thing is, okay. So this is the complexity theoretic view. Hi, Priya Ranjan, could you please mute your could you please mute your uh, Google Meet? Right. Hello, can you hear me, Mr. Priya Ranjan Raj? Okay, I'll mute. Okay, 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 okay. He left the meeting. Um. Yeah. Anyway, where were we? Okay. So okay, we have this loose upper bound that IP is contained in P space. Now, question is, can we make this better? So that is another thing. And Suraj, you just said that IP is equal to P space, right? So okay, so that is good. Next, what we want to do is we want to show other generalizations also. Like, what if let's say the prover this time is deterministic, sorry, non-deterministic. Do we know anything about it? And not by not non-deterministic, randomized. So do we know anything about it? Or let's say the randomness, okay, by the way, okay, and you may have seen this in the lectures. Verifier is random, okay, but in the standard definition of IP, prover is not able to see what kind of random coins verifier tosses. Okay, verifier tosses a few coins, but prover is not able to see. What if prover is able to see? What is called a public coin protocol. So then you have Merlin, Arthur, Arthur Merlin, and so on. So how powerful are these protocols? That is another question that we are interested in tackling. So this is some of the complexity theoretic views, okay, of interactive protocols. And but yeah, so let's move on. Okay, so here's the question. So the question is as following. Oh, okay, I should have made a list, okay, instead of, okay. So the question is, which of the following is true about interactive protocols? Okay, the permanent can be computed by a polynomial size interactive proof. DIP is contained in P space. BPP is contained in IP. AM poly is strictly contained in IP. So look at it once, Suraj. Okay, and just let me know if you have any answers. Oh, okay. 2, 3, 4. Okay. This is 1. This is 2. This is 3. This is 4. Okay. 2, 3, 4. Um. Okay. DIP is contained in P space. BPP is contained in IP, and AM is contained in AM poly is contained in IP. Okay. 1 is not true. So why is 1 not true, Suraj? Any idea?
Sir, about one, I don't know. So that's why
Oh.
I'm not marked one.
Okay, okay, okay. Yeah, sure, no problem. Yes, but okay, I'll ask you a question. But is there something interesting about permanent? Um, is it complete for any class? Is permanent complete for any complexity class? Hello, okay, I think. Were you trying to speak? I cannot hear you because yeah, yeah, Suraj, this is getting muted.
Sir, maybe uh, Sharpie.
That's right. Exactly. Right. Good. So permanent is complete. Okay. Permanent is complete for Sharpie class. And what about Sharp reset or Sharp sat, Sharp reset, whatever? Is it also complete for Sharpie?
Yes, sir.
Yeah, right. Because that is how we showed that permanent. We did a reduction, right? Sharpie class. So what did we see in the lectures? What we saw in the lectures was Sharp reset. Okay, can be computed or is in IP, right? I forgot who came up with this result. Uh, it's not. Anyway, but you get it. Sharp 3 sat is in an IP, and Sharp 3 sat is Sharp P complete. And permanent also belongs to Sharp P. So what does it mean? It means I can take the reduction. Yeah, exactly. It's true to a polynomial reduction. So what I can, yeah, exactly. what I can do is I can take the reduction, take the, let's say, permanent, okay, reduces to 3 sat, sharp 3 sat via a reduction sigma, and that what I can do is I can solve 3 sat first. What I can do is I can turn permanent problem into a 3 sat problem via sigma. Okay, I can take the matrix for that n cross n matrix for sigma and turn it into a 3 sat instance, sharp 3 sat instance. I'll make it into a circuit, and then I'll pretend as if this is my input, and then let the interactive protocol go on. And then if it accepts, then I accept. Sorry, if it gives a certain count as this is the number of satisfying assignments, then I'll say the permanent has the same number of satisfying assignments. That is the equal to the permanent. And if yeah, but it's a counting problem, so there is no yes or no involved. Okay, but still, this shows that part one is true, correct. Okay. So permanent can be computed by polynomial size interactive protocol. Good. Next, DIP is contained in P space. Okay. Deterministic IP is contained in P space. Now, uh, any idea?
Sir, I think because verifier is here deterministic, so he can give maybe deterministic size only uh, random numbers. So transcript will also be means of some fixed size only in n, maybe polynomial in n.
Yeah. Okay. And what do you do?
So that's why it belongs to P space.
Oh, but what about how do you take care of the randomization? And how do you simulate provers? So you need to say like for you need to check for all provers, right? Or you need to check for that one prover for which verifier accepts with a high probability, or you need to say that, oh, none of these provers actually. But you are close, close. You said that the transcript is polynomial. Yeah, that way we can prove. But I'll talk about more in detail later. Okay. And but yeah, that is one way to do it. But another way to do it is again that DIP is contained in IP actually, but this IP is equal to P space as you said, right? So DIP is contained in P space. So two is true. And BPP and IP. Yeah,
So maybe because IP definition means BPP definition is inside only the IP definition.
that is correct. That is correct. In fact, yeah, good. In fact, you can even say that BPP is actually equal to IP with no interaction, no rounds. Just like NP is IP with one round of interaction, BPP is IP with zero rounds of interaction. Okay, that is, I don't need to send any questions itself, because what do I have here? I have a prover and I have a verifier, and I want to check if X is an L, and verifier is randomized. So he'll toss his random coins. Okay, he'll toss his random coins and then run the BPP algorithm on those random coins, and with probability at least 2/3 he'll accept, or at least at most 1/3 he'll reject by simulating the BPP algorithm, which is exactly the definition of IP. The other way around is also fine. I have the IP protocol, Since the verifier's randomness, I can simulate it by the BPP machine and continue. This will give me a BPP algorithm, which will accept with at least two-thirds probability or reject with at most one-third probability. So BPP is actually IP where verifier does all the work. There is no need for prover to do anything. Okay, so this is also correct. Now AM poly is contained in IP. It's strictly contained. Now you had said yes, right? So uh, what may be the reason? Okay, what is AM? First of all, AM is Arthur Merlin protocol, right? So Arthur Merlin is just a fancy name. Arthur is the verifier. Merlin is the prover. Okay, and here this is a public coin protocol. This is a public coin protocol. Okay, what is IP? IP is a private coin protocol. What does private coin protocol mean? Well, um, prover cannot see the random bits of the verifier. Okay, prover cannot see the random bits of the verifier, and public coin obviously means that the coins you toss, it will communicate that to Arthur. That is the sorry, to Merlin, the prover also. Okay, now private coin protocols are seem to be a bit more powerful. Okay, because using the help of by using the help of randomness, you can actually do a lot. For example, solve graph normalized problem. Right? You can see that using randomness, you are strict, no, not strictly, but you are more powerful than NP. Okay, but look at AM. Okay, it is a public coin protocol, so you are actually informing what kind of random bits you toss. So it may actually work against you, right? Now the prover, which is the cheating prover who's trying to fool you, may see the random bits you toss and then accordingly change its answer so that it's trying to fool you, right? Now, but what did we see? We saw that um, AMK, okay, is equal to IPK plus 2. So you can change um, public coins to private coins with at most 2 more rounds of interaction. This is from the lectures. Okay, it's there in the lectures, and you can check it. That it is very interesting that actually any public coin protocol can be made into a private coin protocol with just 2 extra rounds of interaction. Okay, so this is a very interesting thing. So what do you have? You have that AM poly is nothing but IP poly plus 2. Okay, IP poly plus 2, or So I can make it looser by saying it is containing this. Okay. It's contained in IP poly plus 2. Okay. Oh, sorry. No, it's not called it equal to. Sorry. Equal to IP poly plus 2. Now what is this? This is nothing but still polynomial, right? Is equal to IP poly. So AM poly is equal to IP poly. So why is it a proper subset, not equal? Yeah, that is the question. That is the thing. This is wrong because here it's written a proper subset, while it should be a strict. It should be a non-proper subset because they are the same thing. AM with polynomial rounds is equal to IP polynomial rounds, which is equal to IP. Okay, AM poly is equal to IP. Therefore, AM poly is contained in IP, not strictly. So 3 is false. Is that fine, Suraj?
Yes, sir.
Okay. Yeah. So okay, that was the first question. Okay, let's look at another question. So yeah, here's another question. Okay. So another question about why is this model the more natural model? Okay, because we made the verifier randomized. Now, what if we make the prover randomized? Okay. What if we make the prover randomized? Is there any advantage to it? So the question says in the interactive proof model, the verifier is randomized. Show that the model is not made any powerful if the prover too is said to be randomized. Let's say the prover is also allowed to be randomized. So is there any advantage here? So that is the question. And we have said that no, the model is not made any more powerful if the prover is also said to be randomized. Okay. So any idea why?
Sir, maybe because even if the prover is randomized, to find the correct path in the graph, uh, random random numbers will not help much.
Find the correct. Okay. Okay. Close. But okay. One thing I want to ask you. Okay. That is what is the complexity of the prover? As in what do we? Okay. Verifier we have in the definition of IP. Verifier we've assumed it to be deterministic polynomial type. Sorry. Probabilistic polynomial type. Right. Verifier is a probabilistic polynomial type machine. What about the prover? How powerful is he? Is he restricted in terms of space or in terms of time? Exactly, all powerful. We call him all powerful, right? So verifier is all powerful. So what does all powerful mean? All powerful means that let him take as much time as you want. Okay, or in other sense, in another way to think about it is, let's say he can compute even things like NEXP. Okay, something that takes exponential time languages and just constant time. Okay, in just one step he can do it. Okay, so something like that is what we mean by all powerful. So if you make the prover randomized, you are correct in a sense that it is not adding to us anything because the prover is all powerful. So randomization does not help us here because let's say the prover is in BPP. Okay, then we are only making the model more restrictive. Okay, because already we are saying that prover can compute anything in any XP or P space or whatever, right? It can take as much time and space as he wants. Okay, but it so happens that even if sorry, okay, prover is all powerful. The prover is all powerful. Now it so happens that um, Any randomization will not add to its power. Why? Let's say, suppose prover is randomized. Okay. And so, what do I mean by randomized? Well, prover is able to toss some coins and make its decisions. Okay. So, let's say this is the prover P and it tosses coins. Okay. And these are the different outcomes and so on. And it wants to maximize its chances. So these are its good chances, okay, where the verifier will accept, and these are the bad chances where the verifier will reject. Well, since the prover is all powerful, it can explore all these paths in any amount of time at once, okay, even exponential time, and it can just send this, say, okay. So since prover is all powerful, okay, it sends the most optimal transcript to the verifier to maximize its chances every time because it can calculate it in no time. So therefore, it does not make sense actually to make the prover randomized. It is as good because here there is no randomization happening. You are actually going across all random bits, all possible random bits. Just one minute. Okay. Okay. Good. So okay. So we are over with the session almost. Okay. Very quickly, but it's fine. So Shamir, okay, in 1992 showed that IP is equal to P space. Okay, prove the forward direction of the containment IP is that is IP is contained in P space. So yeah, this is an interesting take that around okay actually I think around 1990 Shamir showed it, and around 1980s okay sharp 3 sat okay uh, is in IP is what was shown. Okay, sharp 3 sat is an IP is what is shown, that is sharp p is contained in IP. And okay, let's give credit to the authors. Okay, sharp 3 sat IP. Yeah, Nissan. Okay, LFKN. Nissan and all showed in, yeah, if you see this, okay, if you see this, this is done in 1989. Okay, so this is in 89, and this result was of 1990. Okay, just 1 year apart, and shown by Shamir because Shamir is a famous cryptographer. Okay, these are all complexity theorists. Okay, but Shamir is a cryptographer. Okay, and LFKN they showed this very interesting result that oh you can actually do 3 sat. IP is very powerful. It's much more powerful than NP it seems, and Shamir looked at the proof and then he thought about generalizing this process. And I mean, it is said that as soon as this was published, Shamir thought about it, and then he replied a mail to them saying that okay, IP is equal to P space, and then published it. And well, I mean, and these fellows LFKN that they were uh, I mean, very surprised and at the same time disappointed that they did not get to it, even though they were so close. So you've already seen the proof to 3 sat as in sharp 3 sat as an IP in the lectures. And okay, Shamir generalize the idea, okay, in the other direction. What we are trying to say is in the forward direction, which is a simpler direction. The harder direction has some extra work which I didn't want to do today, so I did not work it out. Also, if I knew that I had so much time, I would have done it today. But they use some he used some kind of algebraic techniques about Chinese remaindering and arithmetization of formulas and so on. And he showed that TQBF, this totally quantified Boolean formula, which is p-space complete, can be actually solved by IP. Okay, and I mean the argument is not very clean, but he was actually successful in showing this, and this was a huge result. You can actually to say that interactive protocols is equal to p-space, that was a very huge result. I believe there is a quantum version of IP also, which is called QIP, and I think it was a few years ago when QIP was shown equal to p-space. Okay. Anyway, let's go on with the proof. So I want to show that IP is contained in p-space. So you had a very close idea to what was there. Okay, you had a very close idea about showing that IP is contained in p-space that time. Okay, and what I want to do is I want to say, okay, so let's say L is an IP. Okay, so there exists an interactive protocol. Okay, interactive via an interactive proof system, and I will call it. I won't call it P because it sounds like prover. I'll call it pi. Okay, let's say via an interactive proof system pi. Okay, I want to show that it can be, and claim is that pi can be simulated in polynomial space. Okay, pi can be simulated in polynomial space. Now, how do you do that? Well, p space is a very powerful class, so you may think that it is quite straightforward to do it, and that is true to some extent, but there are some problems with it. Okay, so let's look at the definition of IP. Okay, so IP means that if X is an L, then this uh, there exists a P, prover P, such that the verifier, on interacting with the prover, outputs a yes with at least probability at least 2/3, and if X is not in the language, then give me any prover. Okay, any cheating prover will not be able to fool it with good probability. Okay, so this is what I want to calculate. This is what I want to do, and I want to simulate this. So, and the probability is over the random bits. Okay, the random bits are sampled across some polynomial size distribution. Okay, and so this is what I have, and okay, so what I can do is, okay, so here is the idea. Go across all provers and go across all possible random bits. Go across all provers and go across all random bits. But that is very strange, right? Because what do I mean by go across all provers? Because prover is all powerful, so I cannot possibly encode all types of Turing machines and then try to show it, right? And going across all kind of random bits, that's fine. Okay, so but the main thing to note here is, and which is the key to the argument, is that I do not need to go across all provers. What I can do is I can just go across all of the transcript. This is impossible. Okay. Instead, what I can do is go across all transcripts. Okay. Instead, what I can do is I go across all possible transcript, and why? Because this is polysized, and what are we simulating it in p space? So I think that time you had mentioned also you go across all transcripts, right? So I just wanted to make the idea clear that why are we going across all transcripts? Okay, why is it enough to go across all transcripts? Okay, now what do you do? Well, okay, for each transcript, okay, let me call it tau. Okay, in 0 1 to the whatever the polynomial first polynomial was, let me call it poly prime n. Okay, or p of n, p of n. Okay, for each transcript p of n. Okay, this represents the prover. Okay, this represents the prover. I Now what do? I have the transcript in hand. Now go across all random bits r in 0 1 to the 0 1 to the um, some qn, whatever the size, the number of random bits for each transcript tau, and for each r, what do? I run the verifier algorithm on this transcript and this randomization, and check if it outputs one or not. Okay, so now I did that. Okay, now I go across each random bit. Okay, and now uh, if accept, okay, then what do? I take a sum equals sum plus 1. I maintain a counter. Okay, otherwise I reject, do nothing. Okay, now I keep doing that. Now see that this probability is counted over R. Okay, not across P. For P, it's only there exists. Okay, for R, for yeah, if there exists a P where the probability over R, okay, is at least 2/3. So now the probability should be compared only for R. Okay, I hope that is clear. So sum equals sum plus 1, and you keep doing this. Okay, and now what you do is, okay, you finish this. Now what you do is, now here, once you do it for all R, you compute the probability. Okay, check if, okay, check if this sum divided by all the random bits. Okay, that's how you'll find the probability. Okay, 2 to the qn, because you're going across all the possible random bits, is at least 2/3. Now what does the definition of interactive proof say? If it is at least 2/3 for even one, for even one prover, then I'm supposed to accept. Then accept. Okay, this is what my p-space machine is doing, and okay, and you do this. Okay, and this for loop will go on. This for loop will keep going on, and accept and exit and hold. Okay, and if not, let's say none of these actually accepts the probability of greater than 2/3. Okay, for each of the random bits it is at most 2/3. Okay, and we do so for each prover. For each prover we do that. Okay, and okay, I made a mistake. This should be till here. So once the for loop ends, right? And I want to check, yeah. And now this is ending here. Okay, this is end for. This is end for. Now that both ended, now I'll say that, okay, none of the transcripts, that is, none of the provers, were able to make the probability greater than uh, uh, less than greater than 2/3. So it must be that by the definition of IP, okay, none of the provers could do it. So I will reject. reject, and hold. So this is the algorithm. So how much space do I take? I take tau plus r plus how much ever space v is taking, right? So space taken is the space taken by tau plus the space taken by the random bits plus the space taken by the verifier v. And this is polynomial. Okay, this is polynomial. This is Pn. This is Qn, which is also polynomial. Plus p is taken by the verifier, and the verifier is a non-deterministic polynomial time machine. So it's an NP machine. So it is already in p space. So this will also take polynomial time. So which means polynomial space. So therefore, IP is continuing p space. So this is one direction of the proof. Okay, and this is a simpler direction. The other direction is much more complicated, but it closely uses the idea of sharp three is contained in NP, can be solved in NP, and therefore you have this that IP equals P space, which is a very well celebrated result. Okay, so okay, I don't have any more content after that. So if you have any questions, Suraj, or was it, or let me know if you want me to explain anything. Diagonalization, in short, it is a confusing topic. Okay, sure. Okay, diagonalization. Okay, sorry. Okay, okay, I'll quickly explain diagonalization. So, diagonalization, okay, is a popular technique. In fact, this is how Turing proved that halting problem is undecidable. Okay, so let's go back to the simplest explanation of diagonalization. Okay, and that is um that that the set of natural numbers, okay, is not equal to this set of real numbers. Okay, one is countable, the other is uncountable, and this can be listed. This cannot be listed. Okay, cannot be listed, as in I cannot write one after the other, and that is the heart of the argument of diagonalization. Always that you cannot list them. Okay, so I'll show you what I mean by that. So here's the proof that there are the set of real numbers is not equal in size or comparable in size to the set of natural numbers. Okay, I think you've already seen this proof once, but I'll write it once again. And that is what is, assume that the set R is countable. Assume that real numbers can be counted. Okay, that is, they can be listed. What does it mean? This means there is a way to list it. To list it. Okay, what do I mean by listed? I mean that so that all of them appear on the list. For example, I say, okay, here's the list 1, 2, 3, 4, 5, and the scheme is that every time I add a 1 to the previous number, and then keep going through. This is a list, infinite list. Give me any natural number, it is impossible to miss it. Okay, 1023. It is impossible to miss it because 1020, because of the listing scheme, 1023 will always be present. but it is not so straightforward. But hence I can say it is countable. Okay, and similarly I can do the same thing for even numbers, set of even numbers, and so on. I can do it for rational numbers and so on, but it is not possible to do it for real numbers. Why? Because suppose I assume that R is countable, so there is a way to list it. So suppose here's the list. Here is the list. Okay, so here's the list. I say this is a set of real numbers, right? So here the first number is 9.83257642 and so on. And the next number is 1.93278664. The next number is 7.65 45576 and so on. It keeps going on. This is the first number, this is the second number, this is the third number, this is the fourth number. And I claim that claim is that no real number is missed. No real number is missed. That is my claim. And how do I ensure that? Okay, no real number. That is my claim, which I want to contradict. Okay, which I want to contradict. Okay, so for the sake of contradiction. So what do I do? The idea is as follows. I take the first number from the first row, first digit from the first row, second digit from the second row, third digit from the third row, fourth digit from the fourth row, fifth digit from the fifth row, and so on. I keep doing this. And see, you can already see that this is an infinite sequence, right? This is an infinite sequence. And now I obtain another infinite sequence. Now I take that diagonal and take it out. Okay, I take it out. So I get this 9.95. Let's say this was 7 4 7 4 and so on. This infinite number. Well, maybe if I look for it in the list, maybe it exists. Okay, maybe it exists. Okay, but here's what I do now. Okay, here's what I do now. I add 1 to it, to each digit. If it is a 9, then I'll make it a 0. Okay, so this becomes 0.0685 and so on. 0.0685. This is my new number. Find it in the list. You will not be able to find it. Why? Because this infinite number is touching every row. It intersects with the first number here. It intersects with. It is touching every row. I mean, it was constructed from every row. Okay. So the first digit of this number differs from the, definitely, because I added a 1 to it, 1 mod 10. I added a 1 mod 10 to it, to each of the digit. Okay, I get a different number. Okay, and I added another to the second digit. Okay, I added a plus 1, so it will definitely differ from the second. So the third digit will definitely differ in the third digit in the third row, and so on. So what does it mean? For all I, okay, this number n differs from row I, okay, in ith place, at ith place. For all I, n differs from row I at ith place. Right. So this means that for every number in the list, it cannot be that my number appears in the list. For every, if I place it here, then somewhere it will always differ. If I place it here, then somewhere this new number will always differ. So I have come up with a number which does not belong to the list. But my assumption was, okay, this was countable. So there should be a way to properly list it. But that means my assumption was wrong. It is not possible to list it. And therefore, the set of real numbers, okay, the set of real numbers is not countable. Okay. Now, you can extend this idea. You can extend this idea to Turing machines. Now, the idea about Turing machines is that Turing machines are finite strings. Okay. So you are able to list it out. Getting it? So finite strings, so you are able to list it out. Okay. And because Turing machines can be described by finite length strings. It cannot be described by infinite length strings. Remember that, because you cannot have a Turing machine with an infinite encoding. Your machine will never be built only looking at the encoding, right? So you have a finite length string that describes it. Okay. So what you do is, um, so you can do a variety of things with it. Okay, using diagonalization, and it is mostly used to show relativizing proofs. Okay, you have, okay, so you have a list of Turing machines. Okay, you have a Turing machine which is described by the empty string, let's say. Okay, it may not be true that you can always describe Turing machine as an empty string, but bear with me. You have a Turing machine 0, 1, 2, or not 2, sorry, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on. So this is a list of Turing machines, right? And so to apply diagonalization, okay, so epsilon 0, I write it on both sides. 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay. And so solving the halting problem. How do I solve the halting problem? Okay. Claim is, halting problem is not claim, this is the theorem. Halting problem is undecidable. Right. That is, there does not exist a Turing machine which can tell given a machine whether it halts or not. Okay. So here is the popular idea. Okay. One side what you take is the Turing machines, and one side what you take is inputs. Okay. So you want to show that halting problem is undecidable. So that is, but I want to contradict it. So what I do is assume, for the sake of contradiction, that HP is decidable. So what does it mean that HP is decidable? It means that given a machine M, let's say it is via a machine uh, M. Okay, via this given via machine, given a machine N and its input and an input X, M can decide if N halts on X. So imagine this M to go across all possibilities of N and X. Okay. So if such an M exists, okay, if such a magical M exists, which can solve, given any machine and an input, corresponding input to it, it can solve it. It can tell whether, not solve it, it can tell whether it belongs to the whether sorry X, whether on input X N will halt or not on it. Okay, that is, M can decide if N halts on X. Okay, so M, think of it as an entry filling machine. Okay, M fills entries to the table. What table? This table. So what will it fill? Okay, to the table. That is um um okay. I'll write it in the opposite sense. This is inputs. This is Turing machines. Okay. Now that is um ij. I'll call that matrix as A. Okay. Ij is equal to 1 if machine I halts on input j and 0 otherwise. That is machine encoded by this I, if it halts on 0, okay, here, then I'll say a 1, otherwise I'll say a 0. Otherwise, let's say machine epsilon described by epsilon does not halt on epsilon, then I'll write a 0. And then I start filling. Okay, I start filling these entries. Okay, now my claim is that my machine M, which is going across each cell and then telling, oh, okay, so this is the machine, this is the machine 1 1, and this is my input 0 0 on 1 1 input 0 0. Okay, it halts. That is what machine M is able to solve halting problem, and it says, oh, okay, okay, then I'll write a 1 there, and then it keeps doing this. And my claim is that the machine is able to fill the entries for all Turing machines and all inputs. Of course, it will run infinitely, no problem. Okay. Uh, uh, okay. So actually, it is not the exact M. M is like a subroutine here. So there is a bigger machine K, let's say that can so K. Okay, machine K is an entry filling machine which uses M like a subroutine. Okay, which uses M like a subroutine. It asks M whether this halts on this input and this machine and so on. It does that, and it should be claim is that it is able to fill the entire table for every machine here. Okay, that is what the claim is. But now my claim is that this is not possible. Okay, claim Aij, sorry, not Aij, K fills entry for all given enough time for all n comma um, x. But that is not possible. Why? Because now we'll apply the diagonalization. We'll look at the first. We'll look at the first row, first column. Then second row, second column. Third row, third column. Fourth row, fourth column. Fifth row, fifth column, and so on. I get a string from it now, an infinite length string. Okay, 0, 1, 1, 1, 1, 1, and so on. Okay, okay. So all the diagonal. Okay, let me make one of them 0. Okay, this is 0. So 1 1 1 0. Okay, 1 1. So yeah, this may appear in the list, no problem. But now what will I do? I will flip this. I will flip this to a 1, this to a 0, this to a 0, this to a 1, this to a 0, this to a 0, and so on. Now, this kind of entry filling will never appear on my list. Right? This kind of entry filling will never appear in my list because the this string differs from the first row in the first column, second row in the second column, third row in the third column, and so on. First row, first column is a 0. I have a 1 here. Second row, second column is a 1. I have a 0 here. So it differs from each of them. Infinite length string, of course, but it differs from each of them. But now the question is, I can always trivially design a Turing machine which will follow these kind of this kind of behavior, right? On epsilon, it halts. On 0, it does not halt. On 1, it does not halt. On 0, 0, it halts. I can trivially design that machine. Or in fact, that machine will always exist, which has this behavior. Okay, this that kind of machine will always exist that has the behavior. So how come my entry filling machine was never able to find it on the table? My entry machine was never able to write a row that has this particular behavior, but I can always have a Turing machine which has this behavior. But according to my assumption, um, the Turing machine, I mean, the entry filling should happen for everything. So this is the diagonalization argument that Alan Turing came up about. Okay, I mean, his was not in this design, but internally this was what was happening. Okay, and then you can extend this idea, but the core idea remains the same. Now you can think about what if oracles were there. So even hoarding problem is still undecidable when you take oracles. Okay, and so you have this kind of generalization built upon this core idea. Okay, of taking the diagonal and then flipping the bits. So I recommend you check this BGS theorem once more. Okay, Baker-Gill-Soloway. So there, now that you have this, maybe you will understand this BGS theorem that diagonalization in NP versus P. Okay, how does it help to prove that they do not relativize? Yeah, Suraj, is this clear?
Yes, clearly.
Okay.
Now
Uh,
it's more.
yeah.
Sir, now it's more clear.
Oh, okay, great. Yeah. Any other doubts?
Yes.
Okay, okay, great. So uh, tomorrow, okay, I'll be holding an extra session. Okay, I've informed Goel also last time. Tomorrow I'll be holding an extra session at 4 p.m. Okay, 4 p.m. to 5 p.m. It'll just be a 1 hour session where I'll be giving a summary of the topics of the entire course, and it may help you in the exam. So, have you registered for the exams, by the way, Suraj?
Yes, sir.
Oh, okay, okay. So it may help you with the exams there. And another thing is, I want to have like a short session where I want to talk about some of the, hot topics in complexity theory right now. What are the current research things happening right now? So I am hoping to cover all of those in 1 hour. Let's see. But tomorrow it's 4 p.m. So try to make it, I would say. Okay. And but nonetheless, the recording will still be uploaded. No problem. But if you have any doubts tomorrow, we can again handle it also. Okay. So when are the exams, by the way? 20, 27th. Okay, okay. 27th. Okay, okay. Great. Then, so what is the date today? 15th. Okay, so there is like almost 2 weeks. Yeah, something like that, right? Less than 2 weeks. Yeah, but it's okay. Okay, so prepare well for that. Okay, and try to attend tomorrow's summary session. It will be happening at 4 to 5 p.m. Okay, and okay, then I guess we can stop at this point. Okay.
Thank you, sir.
Okay. Thank you, Suraj. Bye.